Hi everyone, and welcome to another seminar at Physics Latam. Today we have the honor of having Professor Steve Simon with us. He is Professor of Theoretical Physics at Oxford University and a Fellow of the Somerville College, formerly a Department Director at Bell Laboratories. Professor Simon is interested in condensed matter physics, topological quantum effects, quantum information, wireless communication, semiconductor physics, fractional quantum Hall effect, which is the topic of today's talk, and topological quantum computation. His current research focuses on topological phase of matter. He is a fellow of the American Physics Society. It has recently held a Royal Society Wollstonecraft Merit Award. He is author of many popular introductory books on solid physics state and topological quantum. If you have any question during the talk, please raise your hand. And without further ado, I leave you with Professor Steve Simon. Please go ahead.
Okay, thanks. It's a pleasure to be giving this talk. So I'm going to talk about quantum Hall effects, and it's sort of a truth universally acknowledged that all talks about anything topological in condensed matter have to start with integer quantum Hall effect, which I understand you've already heard something about. So our story starts in about 1980 with experiments by Klaus von Klitzing. And what he was doing is he was measuring, just happened, come back. He was measuring a two-dimensional electron system, and you run a current through it like this, and you can measure two different voltages, the so-called longitudinal voltage like this, and the Hall voltage like this, V Hall, VH. Let me write that VH here. VH like this. And this was all at very low temperature, less than 1 Kelvin, and in high magnetic field, B, this. The rather remarkable thing is he measured the longitudinal voltage to a very good approximation was exactly 0, like a superconductor. It supports no voltage whatsoever. And the Hall voltage, even more interesting, was h over e squared, h being 2 pi h bar, Planck's constant, 1 divided by an integer, n is an element of the integers, times the current. And this quantization of the voltage in inverse units of h over e squared is extremely precise. By this time, it's been measured, this coefficient here, well, let me write it out, that R Hall is h over e squared 1 over n, or the inverse G Hall, the Hall conductance, e squared over h times n. And in both cases, the longitudinal or conductance or resistance is 0. So this may look a little bit odd. Both the longitudinal resistance is 0 and the longitudinal conductance is 0. That means just the 2 by 2 conductance tensor is off diagonal. So if you invert an off-diagonal matrix, you get an off-diagonal matrix. So if you have zeros along the diagonal and you invert it, you still have zeros along the diagonal. Anyway, the quantization of this number is extremely precisely given in terms of Planck's constant and the charge of the electron to about a part in 10 to the 10 or 10 to the 11. That's a rather remarkable level of precision for an experiment that fundamentally is done in dirty conditions. So you don't know if there's dirt in your sample, you don't know the shape of your sample, you don't know exactly how you attach the contacts in your sample. It's independent of whether you add to the system, if you add interactions between the electrons, if you add spin-orbit coupling to the electrons, if you add phonons to the system, if you add, all of these things turn out to not matter. The quantization of this exact result is precise to 1 part in 10 to the 10. That's like measuring the distance between, here and here in Berlin and my other home in in England to within a micron precision. So it's a crazy amount of precision for a solid state experiment. So we need some strong precision, some strong principle, which is going to arrange that this quantization is so precise. And this strong principle was identified by Bob Laughlin, and it invoked a theorem known as the Byers and Yang theorem. So Yang is Byers and Yang, 1961. Yang is the C.N. Yang, the Nobel laureate who won his Nobel Prize for high energy physics, and the principle of parity breaking in high energy physics. And Byers is Nina Byers. So Nina Byers was actually she was a fellow at my college in Oxford, Somerville College in Oxford. But when she did this work, she had moved to the United States already at Stanford at the time, and she had sort of went back and forth between the United States and Oxford for some number of years. And eventually she converged at a faculty position in Los Angeles, where she spent the rest of her life. I spoke to her before she passed away. She passed away maybe 7 or 8 years ago now. But I spoke to her when before that, and she said that she always missed Oxford, and she thought it was, she was sad about having and being forced to live in Los Angeles for the rest of her life, but she had other family reasons why she needed to be in the United States. Anyway, so that was Nina Byers, who was a rather brilliant theoretical physicist who most condensed matter physicists don't know, because she was mainly a high energy person, as we see in Yang. Okay, so what is this principle? So the principle is the theorem is the following, and the theorem is true with disorder or interactions or pretty much anything. You take any system, it can be a two-dimensional system or a three-dimensional system. This is your system, and you cut a hole in the middle. And then I'm going to take that system, I'm going to stick through it some magnetic flux, like this, call it magnetic flux phi. And this kind of looks like a Harnaff-Bohm effect, if you're familiar with that. The idea is that in a Harnaff-Bohm effect, if you do a scattering experiment around phi, if you change phi to phi plus a fundamental flux quantum, plus a fundamental flux quantum, phi goes to phi plus phi naught. Phi naught is 2 pi h bar over e. The fundamental, that's a unit of flux. If you work out the units, 2 pi h bar over e is the amount of flux. If you change phi by this amount, you get the same interference pattern. Now, the Byers and Yang theorem is the same as this a Harnaff-Bohm effect, but it's a little bit more than that. It basically says that the state of the system is exactly the same when you add this additional flux, one flux quantum of flux. The system is in exactly the same state as you started, because you can just gauge away that additional flux. And we can prove this theorem because it's not too hard to do. So the proof of the theorem is you actually make the gauge transformation. So generally a gauge transformation is you take the vector potential to a vector potential plus gradient of some chi. And if we're keeping track of constants, there's an h bar over e that usually comes here. And if you make this gauge change, the magnetic field is unchanged. You're probably familiar with that. Gauge transformations don't change the magnetic field. Under this change of gauge, the many particle wave function gets changed to, just picks up some factors, I equals 1 to n. These are all the particles in the system, e to the I chi of Ri, like this, times psi of R1 to Rn. So you just pick up these phase prefactors. Now, the key here is if I have a non-simply connected geometry like this one here, where there's a hole cut in the middle, I can choose a gauge change function, chi here, which is m times theta, theta being the angle around the center. Now this, this looks like a non-single valued function, because if you go all the way around, it comes around the center, you get back to 2 pi, not where you started, but where the only thing you care about is locally, the gradient is well defined, and e to the I times chi is well defined if theta goes to theta plus 2 pi. So e to the I times this chi is a perfectly good function, and so is gradient of chi a perfectly good function. So under this gauge change, the wave function is going to transform in this way here. And we can check how much flux is associated with this, this gauge change. So integral ds dot b around the hole, in the hole, is the same as integral of a dot dl around the hole. And that is going to then is going to change the flux. The flux is going to go to this flux plus m times phi naught. And again, phi naught is 2 pi h bar over e. So it's under this gauge transformation, the flux gets changed to flux is phi naught, flux plus whatever integer I used times the flux quantum. Okay, so the statement is that, so Byers and Yang theorem, Byers-Yang, is that this is just a gauge transformation. This insertion of a flux quantum through the center is just a gauge transformation. So the eigenspectrum is unchanged by doing this. So that's a rather important thing. It basically says that if I insert, just like this, if I insert an integer number of flux in the center, the eigenspectrum of the physical system here stays exactly the same. And so Bob Laughlin used this principle to prove the precise quantization of the integer quantum Hall effect. So let's give Laughlin's argument. So here we take a sample, a physical sample here. It can be any material you like, actually, but the requirements are that it has, Laughlin. The requirements is it has to have a unique ground state, and the ground state has to be gapped. So there's an excitation gap between the ground state and the first excited state. And that sounds pretty general in the sense that, it could be a band insulator of non-interacting electrons. It could be a Mott insulator made up of interacting electrons. It can be pretty much, any kind of physical system. And I haven't even required that this thing is two-dimensional, although we're going to be interested in the two-dimensional case. So what we're going to do is we're going to take our two-dimensional system. Let me draw it again here, maybe a little bigger. Like this. And I'm going to put a flux through the middle, phi of t, going through the middle of that hole. And I'm going to change phi as a function of t. Okay. Now, from Faraday's law, if I change phi as a function of t, there's going to be an EMF. EMF epsilon is minus d phi dt. And I can also write that as integral dl times the electric field going around. So the electric field is going around this way. Okay. Now, I know that this thing, since it's gapped and has unique ground state, I know that the longitudinal conductance better be 0. Why is that? The longitudinal conductance. There better be no current flowing in the direction of the electric field. Why? Well, because if there's current flowing in the direction of the electric field, that means there is current and E going in the same direction, and then there's power dissipated. Power is E dot J. If this conductance were non-zero, the longitudinal conductance were non-zero, there would be power dissipated. And power dissipated means that you've somehow excited the system up to a non-ground state situation. The only way you can dissipate power is if you go from the ground state to a non-ground state. And we've presupposed that this is a gapped system. It has a finite gap. So if I have a low enough electric field and therefore a low enough current, I can't make any transitions to any excited states, and I can't dissipate power. So that means if I have and this is maybe not surprising, if I have a system which is gapped, is no low energy excitations, it's an insulator. You can't run current through it. You can't change the system a little bit in order to start current running. It means sigma xx is 0. However, it is possible to have current flowing orthogonal to the electric field. And that's what we're going to try to calculate. So we'll imagine having a electrical contact on the inside and electrical contact on the outside. And we want to see how much current runs perpendicular to the electric field. Now, if the current runs perpendicular to the electric field, that does not dissipate any power, because power dissipated is E dot J, and the dot product is 0 if they're orthogonal to each other. Okay, so how much current runs? Well, okay, so the current that runs in the perpendicular direction is going to be, we'll put the minus sign there, the Hall conductance times the EMF, and we'll write that then as the Hall conductance times d phi dt. Okay, now what we're going to do then is we're going to take phi and we're going to slowly adiabatically change it to phi plus delta phi. Okay, and ask how much charge will be transferred. Well, the amount of charge transferred from the inside to the outside is integral over time from of j of t, and that will be g Hall integral d time epsilon of t. I see I've lost a minus sign. I'm not sure where the minus sign went here, but maybe let me get rid of it here. Come back. Let me just get rid of the minus. One more time. Get rid of the minus sign there. Oh no. Yeah, no. The minus sign was supposed to be here, but I had an extra minus sign there. There. Okay. Good. And that is then GH integral dt d phi of t. Oops. D phi dt. Let's see, the minus sign was supposed to be there, but this is now plus sign, and that will be just GH times delta phi. Okay, so as I change the flux, I move charge from the inside to the outside. It doesn't matter how long I take to change the flux. The amount of charge I move is proportional to the amount of flux I change. Okay, now all I do is I say, let's choose delta phi. Choose delta phi to be a flux quantum. Phi naught. Then I invoke the Byers and Yang theorem. At the end of the increase of the flux, so I start in a unique ground state at the beginning of the day, and I have some eigenstate. I insert a flux quantum. I adiabatically track the ground state. It's gapped the whole time. At the end of inserting this flux quantum by the Byers and Yang theorem, I'm back in exactly the same ground state. So because I've inserted one flux quantum, so I get back to exactly the same ground state. So get back to exactly same ground state. Same ground state. Ground state. Okay, so that means the only thing, so the spectrum comes back to exactly the same spectrum that I started with, and the ground state goes back to exactly the same ground state. So the only thing that could have possibly happened in that process is that I could have transferred an integer number of electrons, we'll call that integer number p, from the inside of the system to the outside of the system. And that is then going to be GH times the flux quantum, like this. And that's GH, they'll put in the expression for the flux quantum, 2 pi h bar over E. 2 pi h bar is just h. We'll just take this equation and simplify it, and then we get GH is P, an integer, times E squared over Planck's constant h. Okay? And it doesn't really rely on anything about the microscopics of the sample and what the microscopic interactions are, if it had spin-orbit coupling, if there was gravity on the sample, if there were phonon. The only thing it requires is that you're in a unique ground state the whole way through. And when you insert the flux, you get back to the original state that you were in. Okay? So what you're really doing is you're doing some sort of spectroscopy on the charge of the electron, on charge of E. Charge of E. Charge E. In other words, in this procedure, you can transfer one electron from the inside to the outside, or two electrons from the inside to the outside, or three electrons, but it's quantized in units of the electron charge. Now, it may be the case that P is 0, in which case there's no Hall conductance and you don't transfer any charge at all. But what von Klitzing discovered is that in two-dimensional electron systems in high magnetic field, P is non-zero. You can get a non-zero result. And it's now been shown just in the last couple of years, actually in the last year, that you can even get, well, no, in the last 10 years, you can get situations where even in the absence of magnetic field, even in total externally applied magnetic field equals 0, you can have P not equal to 0. Now, there has to be time reversal symmetry breaking somewhere, because you transfer the electrons from the inside to the outside, not the outside to the inside. There's two different possibilities. So there is a symmetry breaking that goes on, but that can happen spontaneously. You don't have to apply external magnetic field in order for this to happen. So this has been shown to happen in zero magnetic field in a number of different systems: magnetically doped topological insulators, in twisted bilayer graphene, in molybdenum telluride twisted on top of tungsten selenide, so-called moire heterostructures. And generally, this kind of system is known as a Chern insulator. Chern insulator. And this integer P is equal to the Chern number. Okay. All right, good. So having just proven, are there any questions so far? Is everyone happy? Everyone's happy. Having proven that the Hall conductance for an insulator is P E squared over H, it came as a bit of a surprise. And this P is counting number of electrons. This P is counting the number of electrons, is spectroscopy on the charge of electrons. It was a bit of a surprise in 1982 when Tsui, Stormer, and Gossard. I should also mention that von Klitzing won a Nobel Prize. Maybe I'll write this way back up here. Way back up here, von Klitzing, Nobel, 1985. And Tsui Stormer and Laughlin, these two, and Laughlin, who did the theoretical explanation, Laughlin won a Nobel Prize in, 1998, I think. Anyway, so what did Tsui, Stormer, and Gossard discover? They discovered that you can have situations where the Hall conductance is some P over Q, H over E squared, where P and Q are relatively prime integers. So the state that they measured was the so-called Laughlin state. P over Q is 1/3. But there's also 2/5, 3/7. There's lots and lots and lots of these that have been measured, I think, over 100 different fractions. And also this measurement of the Hall conductance is extremely precise. As far as people can tell, it's precise to a part in 10 to the 10 also. So this is known as fractional quantum Hall
Sorry,
effect.
Professor.
Yeah.
Someone posed a question in the chat box.
Yes. Yeah. Okay. Yeah, why is it called a Chern number? What's the complex vector bundle? So it's really, strictly speaking, it's only, people use the word Chern. Okay. It's easiest to see in the case of non-interacting band insulator. And in a non-interacting band insulator, what you have is you have a mapping from K, which lives in the Brillouin zone, which is say a torus, to a set of filled wave functions, psi K, in some filled bands. So you have some number of filled bands and then they're empty bands. So it's a bundle over the base space being the Brillouin zone, and it's wave functions of each. So each K is a state in the Brillouin zone, and then you get a wave function for each K in the Brillouin zone. And the reason it's a fiber bundle rather than a function or a functional is because you can't, you're not guaranteed to be able to describe all of the wave functions in the same gauge. Okay, does that answer the question? I hope. If that didn't make sense to people who haven't heard about fiber bundles, don't worry about it. That's another lecture. Okay, good. All right, so this effect is known as fractional quantum Hall effect. Quantum Hall effect, as compared to integer quantum Hall effect. And you know, in the case where Q is 1, Q equals 1, we call it integer quantum Hall effect, IQHE, and Q not equal to 1 is fractional quantum Hall effect. And it's surprising, being that we had just proven that the Hall conductance has to be an integer times h. Sorry, I wrote h over e squared. This is e over e squared. This is conductance, so it's e squared over h. E squared over h. Did I have that wrong up here? No, it's right up here. Sorry. Yeah, this is correct here. All right. Did I have it right here? Yeah. Okay. Good. So how is it possible that we can break the theorem that we had? Well, there's a couple ways to understand this. One is, and they're sort of equivalent. One way of saying it is that we insisted that the charge carrier was E, but it's possible, and this is what happens, is that charge fractionalizes into E star, which will be E over Q. And each time I insert a flux into the physical system, instead of pumping one electron from the inside to the outside, I pump one of these fractionalized charges from the inside to the outside. And you might say, well, okay, look, that's cheating. There's a legend about Dan Sui. So the legend is, when they first measured GH is 1/3 E squared over H, he immediately said, "Oh, quarks." Now, obviously, he was joking, because he knew that it's a condensed matter experiment. There has nothing to do with quarks, but it's it was actually very prescient for him to have said that, because he realized immediately that if you had charge fractionalization, you could have this. Now, you might say, well, that's kind of cheating, because the physical state is still made up of electrons underneath. And the Byers and Yang theorem applies to electrons, which is the physical theory underneath. So that's not enough to get you around the Byers and Yang theorem. But there's a second part, which is kind of equivalent. This is going to get you around this problem. And that is, we have, and these are very closely related, is that we insisted in the Byers, in Laughlin's argument, that there's a unique ground state. But if you instead have Q degenerate ground states, ground states, then what happens is you start in, let's call them, let's say Q equals 3, and we'll call the ground states A, B, and C. Then what happens is you start in ground state A, you insert a flux, one flux, and instead of going back to ground state A, you go to ground state B. You're guaranteed that you stay in a ground state because you're gapped the whole time. But if ground state A gets transformed into ground state B, and then after adding another flux, one flux, you get transformed into ground state C, and then after adding a third flux, you get transformed back into ground state A, then you can arrange that, that you get, when you get from ground state A all the way back to ground state A, you transfer one electron from the inside to the outside, say. And what happens between A and B? Well, what happens between A and B is that you actually transfer a third of an electron from the inside to the outside, but that's actually changing the structure of the ground state itself, that you've having moved a fractional charge and you're no longer back to the same of the three ground states. So that's going to be the way we get around the Byers and Yang theorem. Okay, so we need to have a situation. So, and in fact, the difference between ground state A, B, and C is simply that ground state B looks like ground state A, which is having moved a fractional charge from the inside to the outside. So how do we arrange such that we get these fractional charges? And how does fractional charge quantum Hall effect come about? So how do we get? We get fractional quantum Halls. Well, let's think about electrons in the absence of a magnetic field. In the presence of a magnetic field. So this is E in 2D electrons, 2D electrons in magnetic field. The system breaks up into Landau levels. So this is lowest Landau level, so first Landau level, and so forth. There's a big gap. And so this is energy in this axis. There's a big energy gap between Landau levels. Just notice that if you fill this entire Landau level here, that's integer quantum Hall effect. And this is the energy gap between the filled ground state and the first excited state is here. So that's an integer quantum Hall effect. In fractional quantum Hall effect, we've only filled the lowest Landau level part way. So fractional quantum Hall effect, we fill, say, let's focus on the so-called nu equals 1/3 fractional quantum Hall effect. Nu equals 1/3 fractional quantum Hall effect. Hold on. There we go. Quantum Hall effect. Okay, nu equals 1/3 fractional quantum Hall effect. We have a 1/3 filled lowest Landau level. And so that means I have to take, I have this macroscopic number of states in the lowest Landau level here, and I need to fill a third of them. So if I want to ask, well, how many possible ways can I do it? It's, okay, maybe I should say that in the lowest Landau level, there are, the number of states equals the number of flux through the system, through the whole system. Or you can say that's also equal to the number of magnetic unit cells. So if you want to think about the electrons in a magnetic field as being like Bloch electrons. You take a region which has one flux quantum through it, you call that one unit cell. The next region with one flux quantum through it is another unit cell, and so forth. And there's one state in the lowest Landau level per magnetic unit cell. So that's the number of states is macroscopically large. So number of flux is the number of states, and I want to fill 1/3 of them. So it's number of flux, choose number of flux divided by 3, and this is some huge number of possible many-body states that I can choose. I can make out of the 1/3 filled Landau level. So I can choose these, I can fill these, I can fill some of these in an enormous number of different ways. And the thing that saves us is the electron-electron interaction is going to chooses a particular ground state, or a set of 3 ground states. Ground state, or a set of 3 ground states. And the idea is we're going to still end up with some ground state and a many-body gap, plus a gap. And in fact, it will be 3 ground states and a many-body gap to all of the excited states. And rather crucially, this gap is, can be described as saying the chemical potential as a function of n jumps, which is exactly what you would get in the integer quantum Hall case. In the integer quantum Hall case, you fill this entire Landau level exactly. So then you fill the single Landau level. You have an integer quantum Hall effect. You have a Chern insulator. And then there's a jump in the chemical potential. The next electron you put in has to go up here. That's a jump in the chemical potential. Okay. But in the fractional quantum Hall effect, you fill up 1/3 of the Landau level. And due to interactions, there's a jump in the chemical potential. It's still a gapped state. Now, I should mention that there's this idea of what they call a fractional Chern insulator. Fractional Chern insulator. Which is basically exactly the same as fractional quantum Hall effect, but instead of using Landau levels, but not Landau levels, you fill up some, you partially fill some band. A Chern partially fill a Chern band of some sort. And the Chern band can look somewhat like a Landau level, some lattice model with a non-zero Chern number, or actually it may not look that much like a Chern number at all, and you can still get fractional quantum Hall effect out if the interaction is appropriate. In fact, a rather surprising result, which I'll just quote, it's a result of paper by myself and Harper, Simon, and Nick Reed, shows that you can get fractional quantum Hall effect in a Chern 0 band. So in fact, the band can be Chern 0. And in fact, if you're familiar with the idea of Berry curvature, in fact, the Berry curvature can be equal to exactly 0. And you can still get fractional quantum Hall effect if the interaction is appropriate. So but sort of morally, what you're doing is you're filling something that's kind of like a Landau level, but it doesn't have to be that close to being a Landau level. It can be a trivial band if the interaction is strange enough. So this is the idea of a fractional Chern insulator. You instead of filling a Landau level, which is just free electrons in a magnetic field, you fill a band of electrons part way. Okay. So, but the simplest example is say a 1/3 filled Landau level, filled lowest Landau level. So it's electrons in a magnetic field, and we fill up the lowest band 1/3 of the way. Now, one thing that's worth pointing out is that if the system has no disorder, with no disorder, and no lattice, then the system is translationally invariant. And you can show that the Hall conductance is always, well, N over B times E squared over H. And that's, that's not quantized in any sense because the density is continuous, the magnetic field is continuous. You can change these things completely smoothly. And the argument for this being true comes from just Galilean invariance. So let's show why this is true. Suppose I apply an electric field to my sample in a magnetic field like this. So I have an electric field in my sample. I have a magnetic field perpendicular to the plane of the sample. The force on any particle is the usual minus E plus V cross B. If I switch to a moving frame with, I guess V is, okay, let's put E in the Y direction. E vector is E times Y hat. And I switch to a moving frame where V is, I guess, E over B times X hat, then the force on the particles are all zero. And it becomes a stationary state. And that means, the current in the X direction is just the charge times the density times E over B. It's velocity, so this is just the velocity. So charge times density times velocity, maybe with a minus sign. And so that means, let's see. So this should give me the Hall conductance here correctly. And so phi naught, let me just change this up here. Phi naught is H over E. And you can see these two expressions are the same. The current En over B, and that's the same En over B. There, okay? So basically, it says if I shift into a moving frame, I get rid of the electric field and everyone stays still. And the reason, and this is true, for any system of free electrons with no disorder, with no lattice, you would always have exactly this Hall conductance. So how is it that I'm going to get this nice quantization of my Hall conductance? Well, the way I'm going to get, this is true for integer and fractional quantum Hall effect. The way I'm going to get nice quantization of the Hall conductance comes from the jump in the chemical potential as a function of density, which we have for integer quantum Hall effect and we have for fractional quantum Hall effect. And then you have to ask, well, in the experiment, do you control the chemical potential or do you control the density? Let's take the simpler case where you control the chemical potential. So if you control the chemical potential, if there's a nice jump in the chemical potential, then there's a range of chemical potential, a range of places where I can put the chemical potential continuously, and the density is completely fixed. Density is fixed. We're having, anywhere I put the chemical potential here, continuum of different places, I fill up this lowest band. So this is E, and this is states. So I fill up exactly this band, and the density is completely pinned. So if there's a jump in the chemical potential as a function of density, then I can fix the density for a range of chemical potentials. I don't have to fine tune the chemical potential at all. The density fine tunes itself. Now, in a lot of experiments, what happens is actually so this is fixed chemical potential. In a lot of experiments, what you actually fix is the density, not the chemical potential. Now here, the reason you get quantization is a little bit more subtle. Here, you rely on disorder. And because of because of the jump, cause of jump in mu of n, what happens is most of the system fixes itself to the special n, where just below the jump. It's the special n. And then any change in the density is accommodated. Changes in density. Accommodated by local excitations that get fixed, get pinned by disorder. This is easiest to understand if I go back to the integer quantum Hall case. So in the integer quantum Hall case, here's the energy, and then here's the density of states. And then, my density of states, now these what were nice thin bands of Landau levels now get spread out into disorder broadened bands. And if I put the chemical potential here, if I put the density sitting right here, put the density right here, if I fill up all these states here, and fill up all these states here, and you might say, well, I haven't completely filled up the Landau band because I have these, a couple holes sitting up here. Don't they cause problems? Don't they change the conductance? And the answer is they don't, because these little states in the tails of the band are extra quasi-particles, extra particles that get stuck on disorder and don't move. So their presence doesn't ruin the perfect quantization of the quantum Hall effect. So it's actually kind of a subtle point that if I have a system without with full translational invariance, I would not have quantum Hall effect. I actually need to have some disorder to pin these additional excitations. Okay, maybe I shouldn't have gone into that level of detail. All right, so now what model are we going to try? Back to fractional quantum Hall effect. There was a question here. So it says, isn't the first case where density is fixed? So, sorry, you're right. It's fixed, right? Oh, up here, this is you control chemical potential, and then N it jumps. So N gets quantized by itself because of because you control the chemical potential, and you fill the entire lowest Landau band here, and if you put the chemical potential anywhere in that gap, so you don't have to fine tune the chemical potential to get the density that you want. That's probably the easier case, although the experimental case tends to be this one, where you actually change the density. Okay, all right. So fractional quantum Hall effect. We still have to. We need a jump in the chemical potential in mu of n. How are we going to see that? And we'd also like to see how we're going to get fractional particles as well. So the Hamiltonian we're going to have, it's a very simple Hamiltonian. There's the usual free particle Hamiltonian, that's the kinetic energy. And then there's going to be some interaction term, V of Ri minus Rj, which we take to be the Coulomb interaction. We'll assume that V is much less than the spacing between Landau levels, so spacing between bands. To a very good approximation, as long as the filling, the so-called filling, the number of Landau bands I'm filling is less than 1, my effective Hamiltonian is nothing more than just the interaction VRI minus RJ in the Hilbert space of the lowest Landau level. So the kinetic energy term here does nothing but breaks the system up into Landau levels, and then the Hamiltonian is once I've restricted myself to the Hilbert space of the lowest Landau level, it's just the Coulomb interaction we're concerned with. Okay. Okay. All right. So how are we going to solve this Hamiltonian? Again, it's a huge problem to solve the Hamiltonian because of what I mentioned way back here, that it's a huge Hilbert space, Hilbert space we're working with. And, you know, your macroscopically big system with however many flux quantum are penetrating the system, and I want to fill 1/3. I have this many orbitals, and I have to fill 1/3 of them, and there's an exponentially large number of possible ways that I can do that. And the Laughlins approach, this is what won him a Nobel Prize, is to basically just guess the right answer, which is always a good thing to do if you have the opportunity to do it. You just guess the right answer and go from there. So the first thing we're going to do is we're going to use a symmetric gauge. So we're going to choose a particular gauge. A is, I guess, 1/2 R cross B. And that's really nice. And then you can just check del cross A is B in the Z hat direction. So R is in the plane. And this is a really nice gauge because in this gauge, the single particle orbitals have a really simple form. There's Z to the M, e to the minus Z squared over 4L squared. Of course, Z is just the complex representation of the coordinate. And L here is known as the magnetic length. L is the square root of H bar over EB. Another way of saying this is that 2 pi L squared is the area of one flux quantum. Okay. So this is really nice. So these Gaussian factors are usually not that interesting. It's these polynomial factors up front which are interesting. And this is true for all m's greater than or equal to 0. So these are all eigenstates of the system. And let me try to show you what these wave functions look like. So what these look like, so here's my two-dimensional system. Here's the position 0. And you know, another way of writing this wave function is psi m goes as r to the m, the radius, then e to the I m theta, that's z to the m, the complex coordinate, and then it's the same e to the minus r squared over 4L squared. Okay, so the phase wraps as you go around the central point here, and then there's an r to the m growth, and then a Gaussian decay. So it's going to be, you're going to get like a little wave packet here, which goes up as a power law, then down as a Gaussian, and it goes around the central, like in a circle around the center. Yeah, it's a terrible circle around the center, but okay, something like that. And it's the radius of this state, if we just maximize, okay, so you maximize the amplitude of r to the m e to the minus r squared over 4L squared, you discover that the maximum, the place where this peaks here, this position, is at radius equals L times the square root of 2m. So what you basically get these concentric rings of these little Gaussian peaks whose radius goes out as the square root of 2m, and the area enclosed by Rm, by phi m, by this radius, contains, okay, the area enclosed is pi times r m squared, which is 2 pi L squared M, this contains M flux quanta. So each successive of these orbitals gets a little bit farther out, each one containing one more flux quantum, and they go in circles around the center and they pick up corresponding phase. Okay. This M index is actually angular momentum. M equals angular momentum. Angular momentum around the center. So the first one has angular momentum 0, the second one has angular momentum 1, and so forth and so on. Okay. All right. And if I fill them all states, I get the nu equals 1 integer quantum Hall effect, IQHE. And the quantum Hall effect I'm interested in is the nu equals 1/3 quantum Hall effect, where 1/3 of the states are filled. 1/3 states filled. Okay. All right. So what was Laughlin's genius? So Laughlin's genius is, if we want to guess the wave, given that we're writing our wave functions, in this symmetric gauge, we want to guess the right wave function. And there's 3 principles that I want to choose. One, the multiparticle wave function, R1 to Rn, is, well, it has to be made up of the lowest lambda level wave functions of these psi m's. So that means it has to be some polynomial in Z1 to Zn, the complex coordinates times a product I equals 1 to n of these Gaussians, Zi squared over 4L squared. Okay, so that's just saying that the wave functions are all made up of these things. Each particle has a Gaussian wave function, and then it will have z to some m, some product of z to some m's. Second, it has to be for electrons, since we're considering electrons are fermions. So, so that means that the polynomial must be antisymmetric. Three, the Hamiltonian is rotationally invariant. So that means it has to be an angular momentum eigenstate, which means the polynomial is homogeneous of degree. So for example, if I write Z1 squared, Z2 cubed plus Z1 to the 1, Z2 to the 4th, both of these terms are degree 5 and have a net total angular momentum 5. Okay, but if I wrote something that did not have a total exponents 5, then it would have a different angular momentum. But since we have a Hamiltonian that's rotationally invariant, the eigenstate, the ground state, should be an angular momentum eigenstate. So it has to be homogeneous with degree. 4, let's see, the maximum radius of the droplet should be, okay, so the maximum radius, that's the maximum degree of any, so I'm going to have some droplet that's going to fill a lot of states in here within some circular region, and the maximum radius should be, well, okay, so we should have the highest power z to the n phi, where n phi is 3 times the number of electrons. Why is that? Well, remember that z to the n phi, this wave function here with z to the n phi contains, where did I write it? Here. and contains m flux. So z to the m contains m flux quanta. So z to the n phi contains n phi flux quanta, and the number of flux quanta should be 3 times the number of electrons. So this tells me how big, how high a degree my wave function should be. Okay, so I have 4 principles. It's a polynomial in z's. It's an antisymmetric polynomial. It's a homogeneous degree, and I know what the total highest power should be. All right, so Laughlin just guessed. And the guess wasn't, I mean, it's in retrospect, it was a very, and maybe it was obvious, but the reason he was able to do this is basically because he took a computer and he diagonalized the problem exactly for 3 electrons. And he looked at the wave function exactly for 3 electrons, and he said, oh, well, that generalizes. And he wrote it down in all generality. So 3 electrons was enough to figure out what was going on. So he wrote it down like this. I'm going to zj, well, to the 3. So this 3 could be any odd number for nu equals 1 over m odd. So we'll choose it to be 3, actually. So for nu equals 1/3. And then the product of over I e to the minus, the Gaussian factors, which we usually don't write. So it's a polynomial. It's good. It's homogeneous in degree. The highest power of z is what? Highest power of any z is z to the, well, okay. So say z1, there's n minus 3 times n minus 1 power of these factors here. These are known as Jastrow factors. And well, okay, Jastrow wrote down factors like this for describing nuclear physics much earlier, but this was the first time it was used in condensed matter. Well, actually, it's not true. It was used in other contexts as well. Anyway, they're called Jastrow factors for whatever that's worth. The highest power of any z is z to the 3 n minus 1. Since n is a large number, we can drop this. So the number of flux is the highest power of z is then 3 times the number of electrons, plus or minus 1. So that's good. And well, okay, and there's one other thing that's really nice. If you change this wave function, so let's generalize this to m, and just choose m odd. This here, m odd. Here, m odd. So this is filling in factors 1 over m. If you choose m equals 1, it's a little bit of an exercise, but m equals 1, you fill all phi m states. You just get a Slater determinant, Slater det of all m, of all phi m's. So you just fill the whole Landau level. So m equals 1 fills the whole Landau level. M equals 1/3 fills 1/3 of the states of the Landau level in some sort of uniform ways. So this wave function, numerically, it's extraordinarily good. It's not exact except for some very special interactions, which I'll discuss next. But there's a couple reasons why it seems to be good. Because you know what the angular momentum is, for each if I think about freezing the position of all of the electrons but 1, and then I move around one of the electrons, say Z1. So then I have a polynomial of some fixed degree, whatever this degree is, and that polynomial has some zeros on the, a polynomial of some high degree has some number of zeros, and a 0 of the wave function is a place where the electrons can't go. The amplitude of the wave function goes to 0 at some point. It means the electron never goes there. And what the Laughlin wave function does is it takes all those zeros and puts them at the position of the other particles. So an electron can't get close to the position of another particle. So effectively, what this wave function is doing is it's keeping the electrons far apart from each other. As two electrons get close to each other, the wave function vanishes very quickly. It vanishes as m powers. So that means there's a very low amplitude of having any two electrons get close to each other. If you have a repulsive interaction between the electrons, the energy is going to be very favorable because the electrons are going to try to stay apart from each other very effectively. Okay, so that's the intuition behind why it is that that this is a good wave function. In fact, Laughlin is exact for a particular form of the wave function. So let's actually, just to make life simpler to think about, let's think about fractional quantum Hall effect of bosons. So imagine we have a two-dimensional system of bosons. And so here, the Laughlin wave function, we can take a nu equals 1 over 2 state. So the wave function is symmetric instead of anti-symmetric. A symmetric polynomial. And well, if I just insert m equals 2 up here, I get a symmetric polynomial rather than an anti-symmetric polynomial. So I can do that by just choosing m equals 2 in Laughlin. And the fractional quantum Hall effect of bosons is actually an exact ground state. Exact ground state of the interaction V of R1 minus R2 is V naught delta function of R1 minus R2. So let's look at that for a second. So the wave function psi equals product I less than j, zi minus zj squared times the Gaussian factors, which I'm not interested in. So the point here is this is a positive definite interaction, can only give you positive energy. And here, there is no amplitude of any two electrons sitting on top of each other. The wave function goes to exactly 0 when any of the two electrons sit on top of each other. So this positive definite interaction is completely zeroed out by this wave function. This wave function makes the energy exactly 0. It's a positive definite interaction. We've made its energy 0. It's the lowest possible energy you can get. Now further, nu equals 1/2 Laughlin is actually the highest density, equals highest density wave function that I can come up with, that you can make, that has this property. For example, if I take a new wave function, any polynomial of z, and multiply it by the Laughlin, let's call this Laughlin 2, and multiply Laughlin 2 by any polynomial of z, it still has the property that it zeroes this wave function out, zeroes this interaction out. So I can take the wave function here, multiply it by any polynomial of the z's, and it still has 0 energy for this interaction. However, by multiplying by an additional polynomial of the z's, that means I've increased the degree of the polynomial. I've made the radius bigger. I've pushed electrons out from the center, away from each other, and I've made a lower density wave function. The highest density wave function I can come up with, which still zeroes out this, this interaction, is Laughlin, where there's exactly, you have a second order 0 at the position of every single particle with respect to the first particle, okay? So the energy, the total energy as a function of density, let's write the density as a density divided by the number of flux in the system. At low density, the energy is 0. You can always write wave functions of this form. But then when you get to filling 1/2, you get the highest possible density state. This is Laughlin at 1/2, at nu equals 1/2. And then for a higher density than Laughlin nu equals 1/2, it's not possible to write any wave function that zeroes the interaction anymore. and the energy goes up. So since the chemical potential is DEDN, this thing then has jumps at nu equals 1/2, which is what we needed. Okay, so at least for this special interaction, you can sort of unambiguously solve the problem exactly and show that the that there's going to be something special happening at nu equals 1/2. Okay, good. All right, let me. Okay, so how do we know that? Okay, in real life, we don't have. Okay, so for fermions, there's another special interaction. V equals V of R1 minus R2 is some V0 del squared of a delta function, for which nu equals 1/3 is the highest density zero energy state. So it's just a generalization that makes nu equals 1/3 Laughlin state an exact ground state. Now, the real physical system, we typically take V of R as Coulomb. And that looks somewhat different from this special interaction for which Laughlin is exact. And in order to say anything about the Laughlin wave function of a Coulomb interaction, you have to turn to numerics. And the numerics tell you that if you take a system with 12 electrons, for example, the Hilbert space size is something like 7 million dimensional. And the overlap of Laughlin with the exact ground state, which you get from exact diagonalization, is greater than 0.99. So it's not exact, but it's really, really close to exact. Okay. All right. Charge fractionalization. We want to look at excitations. And it's actually not too hard to create what they call a quasi-hole excitation. Psi quasi-hole by multiplying psi Laughlin by this factor. What does that factor do? Well, that factor increases each zi by 1 degree. So it pushes, so we have all of these rings, these single particle orbitals like this, and each orbital gets pushed out one. This is exactly equivalent to inserting a flux quantum in the center. So if you sort of adiabatically insert a flux quantum at the origin, you push each, so here's my two-dimensional system. I insert a flux quantum through the system in the center, and each electron gets pushed out one step. And then how much density is left behind? What charge is left behind? Well, the filling is I filled 1/3 of the Landau level, okay? And that means 1/3 of the orbitals are filled. And if now I leave a hole, the lowest, the single orbital at the center is now definitely empty. So I've left one orbital in the center empty. And all other orbitals have a 1/3 chance of being filled. All other have a 1/3 chance of being filled. 1/3 filled. So I started with all orbitals being 1/3 filled. And now it's the one in the center is definitely empty. and all others have a probability of 1/3 being filled. And it's easy to convince yourself that means that the charge, a hole that I left in the middle, is charge E star equals E over 3. Is that obvious? Yeah. Okay. So we've now created a defect with charge E over 3. You can do, oops, come back. There, okay. And in fact, you can put that defect anywhere you like. Actually, another way, well, okay, let me skip that. And we can put the defect anywhere I want. And let me put the defect at some position W by multiplying the Laughlin wave function by Zi minus W times psi Laughlin. So I can put defects at any position I like in the system, and I can actually I can even make multiple defects. I equals 1 to n, Zi minus W1, Zi minus W2, psi Laughlin. And I can put these defects anywhere I like. Okay. All right. So now, I mean, the fact that these excitations, these low energy defects have fractional charge, E star equals E over 3 should be fairly surprising. I mean, what we have is the elementary particles have charge E, but the low energy theory is made up of charges E star equals E over 3. And those would be, if you were a being who lived in this two-dimensional plane and you were at low energy, low temperature, and you would not be able to see the electrons would just look like a soup, and you would only be able to see the defects which have charge E over 3. So this would be the emergent degrees of freedom of the system. Now, and in fact, these charges have been measured extremely clearly in various types of experiments now, starting in the 1990s. It's absolutely unambiguous that the charges are a third of the charge of an electron. So now, the thing that's more interesting is the braiding phase. And this is, I was going to talk about anions. And generally, there's this, we're told this thing in quantum mechanics courses that all particles in the universe are either bosons or fermions, but that's not true. In 2 dimensions, particles can be what's known as anions. Anions. And anions are particles that get a fractional phase, EDI theta, when 2 of them are exchanged. So we know that fermions get a minus sign, and bosons get a plus sign when you exchange 2 particles. But anions can get a fractional phase if they're exchanged clockwise, and the opposite phase if they are exchanged counterclockwise. Okay. So it turns out that these excitations of the fractional quantum Hall effect really are anions. And the experiment we'd like to do, the theoretical experiment we'd like to do, and incidentally, that this experiment has, after many, many years, I mean, this is the fact that these things are anions was proposed first, in 1980, 83 or 84. And it's only just in the last couple of years that people have actually been able to do experiments to measure the braiding phase, where you actually take particles around each other and measure the phase. And now it's been done in several different experiments, rather beautiful experiments. So if I had more time, I would explain those experiments to you. But the experiment we'd like to do is so here I'm looking down on my 2-dimensional system. I take a particle around in a loop surrounding another particle, and I compare it to, let me just make a copy of this. I compare it, and I measure the phase of doing that. Copy, and I'm going to compare that to exactly the same experiment, except instead of having the other particle inside the loop, I put the other particle outside the loop, okay? So we're going to compare the phase and show that the phase you get from doing this process versus the phase you get from doing this process differ by neither +1 nor -1, but some fractional phase. In fact, it would be 2 pi over 3. Okay, so let's see how we do this. So first, I need a digression on Berry's, what is called Berry's phase. So Berry's phase, if you're not familiar with it, it actually should have been called Pontchartrain-Berry phase. So Pontchartrain was 1956, and Berry talked about this in 1984. But it's a correction to the adiabatic theorem. So suppose you have a Hamiltonian that's a function of some parameters R. In our case over here, the parameters are going to be some traps that hold this quasi-particle at this position. So we imagine we're going to move the trap around such that the ground state holds the lowest energy state with that trap there is going to have a quasi-particle that moves around with it, okay? So that's what we're imagining. Then at any fixed value of that position, you have the instantaneous eigenstate psi r like this, okay? And let's assume that these wave functions are normalized wave functions. Now, in fact, Berry's phase, this can be, this is very general. It can hold for any Hamiltonian, which is a function of any type of parameters. Now, what we're going to do is we're going to write psi of t, which is e to the I phi of t. This is going to be some phase times the instantaneous eigenstate, psi of r of t. Okay, so we at any fixed position r, you diagonalize the problem, you get psi of r of t. And what we'd like to do is we'd like to find the prefactor phase out front as you adiabatically change h. Okay, so how do we do that? Well, we just put it into the time-dependent short-order equation. So we have I h bar ddt psi of t equals h of r of t psi of t, like this. And then, well, okay, we'll plug this form into here, and we get minus h bar phi dot plus I h bar ddt of psi of r of t equals e of r of t psi of r of t. This, and then we're going to close it up with psi of r of t on the other side. And then what we get is phi dot equals minus e of r of t divided by h bar minus I, and this is the interesting part, psi of r of t, then ddt psi of r of t. And then we calculate psi at the final time minus psi, phi at the final time minus phi at the initial time is then time initial to time final of dt of e of r of t divided by h bar. This is just the expected dynamical phase. If you have an energy, your phase accumulates e to the I et, e times t. So this is just accumulating a phase associated with the energy. And this is the interesting part, integral dr of psi of r of t ddr psi of r. And you notice that the t has fallen out. This only depends on psi of r now and ddr, okay? So this is known as the Berry phase. Berry phase. And it's independent of how fast I change R of t. I can change R of t quickly or slowly. The total phase that I accumulate depends only on the path of R that I take, okay? So now what I'm going to do is I'm going to try to do that experiment for moving quasi-particles around in the fractional quantum Hall effect. So I'm going to put a quasi-particle here, and a quasi-particle here, or a quasi-particle here, and I'm going to move this quasi-particle around in a loop and calculate the Berry's phase. Okay, so let's do that. So we're going to write down our wave function. And it's going to be a function of two parameters, W1 and it's called W1 and W0. That's the positions of the two quasi-particles. So it's a normalization. I need the normalization such that the wave function is normalized. Then its product I equals 1 to n of zi minus W0, zi minus W1, and then psi Laughlin over here. And we're choosing n such that psi equals 1. And we can also choose that n is greater than 0, greater than 0 everywhere real. And the Berry's phase, just to write it again, in the Berry's phase that I'm interested in is minus I integral as I take dW1 around in a loop of psi d dW1 of psi. And W0 is either going to be inside the loop, back here with the picture. So this is W1 and this is W0. So W0 is either going to be inside the loop or it's going to be outside the loop. In either case, W1 is going to take the same path, but I'm going to either have W0 inside or W0 outside. Okay. All right. So, so what do we do? Okay.
I think there is a question on the chat.
Oh, sorry. Yeah, can it be considered a geometric phase or a topological phase? I think, okay, so people usually call it geometric phase. The word topological phase, I mean, yes, the answer to both of those is yes. Now, the word topological phase is used in several different senses. Sometimes people use the word topological phase to mean phase of matter, not phase like either the I-phi phase. But when they say topological phase, probably what they mean is topological phase of matter. Oh, I see. So actually, let me back up. So, okay, and then let me correct that statement. So geometric phase means it depends on the path. If you want to use topological phase, not meaning topological phase of matter, but a phase associated with topology, then you would mean a phase depending on the topology. So the Berry's phase is actually going to have more than one contribution in it. It will have a contribution. The Berry's phase will have a contribution just associated with the fact that I'm surrounding a lot of electrons there. That will be geometric. But the fact that I surrounded this guy is topological. Either went around this point or it didn't go around this point. But the fact that it went around a certain area is geometric, whereas the fact that it went around a quasi-particle is topological. And the Berry's phase will actually include both of those. So the Berry's phase will include the geometric contribution as well as the topological contribution. And it's a good question, actually. Good. All right. So here we are, and we have to take this derivative. So d psi dW1. Well, okay, we have to worry about the prefactor. So it's going to be d log n dW1 plus, now we're going to take derivative of these guys, plus sum over I minus 1 over zi minus W1 times psi W1 W0. Okay, so the derivative acts on this guy to give me d log n dW1 and acts on these to give me a factor of this. Okay, now the integral dw1 of d log n dw1 is actually going to be just 0, because this is a positive definite number. It comes back to the same result at the end of the path that it is at the beginning. It's basically it's derivative. It's an integral of a derivative, so it's going to give me 0. This one has a singularity in it, so it's going to give me something interesting. So I have to be a little careful. So let's write this out. Let me actually write this out. So psi sum over I minus 1 over zi minus w1 psi. I'm going to rewrite it this way: integral d2x of psi and then a delta function. So a delta function at the position sum over I delta xi minus zi. Sorry, x minus zi. This is only a single x. X minus zi psi, and then 1 over x minus w1. So instead of having a sum here, I'm going to put a delta function here, integrate over x, and have this guy on the outside. I think I'm probably missing a minus sign. I am now the host, or I'm now a co-host. Okay. Okay, so this term here is now just the expectation of the density at position x. Okay, so this is now, well, let me just plug this in up here. So psi dw1 of psi is then, and maybe I'll even put the integral dw, move this over, integral dw1, oops, dw1 here is now going to be integral dw1 around the loop, and then integral d2x of rho of x 1 over x minus w1, and I probably dropped a minus sign somewhere. Okay, with that. And okay, now we'll switch the orders of integration, and you'll notice that the integral of dw1 around this is going to give me a pole, a 2 pi I pole, equals 2 pi I times for each electron I go around. For each electron I go around. So here you have, you're integrating over the density, and you have a loop. If the loop of x, if w goes around x, you pick up a 2 pi I, and for each electron inside that loop, you pick up a factor of 2 pi I. It's really a sum over delta functions, okay? And I think there's an I that I missed. There's a 2 pi I here, and Berry's phase actually had an I in it. There's the minus I here, which that I here is now going to cancel. So I end up getting Berry's phase, phi Berry, equals 2 pi times number of electrons I went around. Number of electrons surrounded in path. Okay, so back to the question that was just asked. So I'm picking up a big Berry's phase associated with going around all the electrons in here. In fact, that Berry's phase is exactly it's the Aharonov-Bohm phase of taking a charge, that's the quasi-particle here, around some flux, because there's actually flux here. It's equivalent. The amount of phase I pick up in counting electrons in that area is the same as taking a charge around a flux in that area. So it's going to be equivalent to the Aharonov-Bohm phase. But you notice that when you put W0 inside, then you have E star equals E over 3 fewer electrons inside. So in this experiment here, there's this experiment here, you've pushed away 1/3 of an electron. So when this guy goes around, it picks up 2 pi divided by 3 less phase. So delta psi Berry equals 2 pi over 3. And this is the final result, that you pick up a fractional phase for surrounding, for one particle surrounding, going in a loop around the other particle. And that's the anion phase. I should stop here for maybe questions. No. So I can, let's see. I have to leave sharply in 24 minutes. In just a couple of seconds, I can say a couple words about how this was measured recently, if people are interested in that. Yeah, no, maybe. So, what are the conditions to the emergence of anions? Well, that's a really good question, actually. I don't think anyone, okay, an anions requires that the low energy theory is a topological quantum field theory. Which means you have to have a long range entanglement. So the ground state has to have some sort of long range entanglement, which the Laughlin fractional quantum Hall state does have a long range entanglement, and its low energy theory is a topological quantum field theory. But, is there, some other statement like how low does the temperature have to be, and what kind of interactions create this? I don't think we have any fundamental rules as to what generally will create anions, except that it has to be something that gives you a low energy theory, which is a topological quantum field theory. Sorry if that's not the best of answers. Are there any other questions?
Yes, I have a question.
Yeah.
This Berry phase would be for like filling fraction 1 over m would be 2 pi over m, let's say.
That's correct, yeah.
Okay.
That was the question? Yeah, okay. Yeah, so for nu equals 1 over m, the Laughlin fractions, the braiding phase is 2 pi over m. There's another question on the chat which says, can this be seen in 3 dimensions? In 3D, all point particles are bosons and fermions. So there are no anions in 3D. But let me try answering that question in a couple of ways. First of all, physically, obviously all experiments that we're doing are in our 3-dimensional universe. We live in 3 dimensions, but we've confined the electrons to strictly 2 dimensions. And the way we do this is by, we use quantum mechanics. In the z direction, you imagine having a z direction, which is out of, okay, so there's an x and y direction in the plane, and in the z direction, there's some potential well. And so there are eigenstates in the z direction. There's a lowest eigenstate and then a, higher excited eigenstates. And the energy gap between the lowest eigenstate and the next eigenstate is sufficiently large that you've basically trapped all of the electrons in the lowest eigenstate, and they have no freedom whatsoever. So the wave function is strictly xyz, is strictly some chi of z times some wave function of x and y. And chi of z is completely frozen, and all the freedom is in x and y. So it becomes a strictly 2-dimensional problem. So that's why we can actually, even though we live in a three-dimensional universe, we can do really strictly two-dimensional physics. Now, maybe I should make a comment about why no anions in 3D. Because this is a good question in 3D. So I won't have time to talk about the experiments, but maybe that's okay. So you know, there's an argument about why why it is that people thought for a long time that we only have bosons and fermions. And the argument goes like this. It's in all quantum mechanics textbook. You take an operator called the exchange operator that takes a wave function psi of R1 and R2 and changes it to psi R2, R1. Now, if you take the exchange operator and you square it, you get back to where you started. So exchange operator squared equals 1. And that means the exchanging, it has two possible eigenvalues. It can be +1 or -1. And if it's +1, we call it bosons. And if it's -1, we call it fermions. And that's the only possibility. But the thing is, in 2 dimensions, let's draw 2 dimensions here and time going upwards like this. If you have 2 particles in 2 dimensions, you can exchange them clockwise and then exchange them clockwise again, like this. And that is distinct from exchanging them clockwise and then exchanging them counterclockwise. And you can see this is true by connecting up the top to the bottom, like this. And you see that this picture over here, we have 2 linked rings. And over here, you have 2 unlinked rings. And these are obviously different from each other. And so the point is that in 2 + 1D, you can't just say exchange. Exchange is not enough information, enough info. You have to describe whether you exchange clockwise or you exchange counterclockwise. And if you have more than 2 particles, you have to say which one's exchanged first and so forth. You can't just say exchange. Now, in 3 + 1D, actually exchange is enough information. And this comes from the following fact. In 3 + 1D, there are no knots in 1D world lines living in 4D. Now, so here we have world lines living in 2 + 1 = 3 dimensions. So we have a knot in my world lines living in 3 dimensions. That's a knot. But there's no such thing as a knot in 1-dimensional world lines if they live in 4D. Now, that's a statement which is completely obvious to some people and completely obtuse to other people. So let me try to make this obvious to everyone. And the way, since I can't, even with the help of an iPad, I can't draw 4 dimensions. So let me argue by lower dimensional analogy. So if I have a 1-dimensional line like this, and I have 2 particles on the line here and here, and I try to move them towards each other and see if I can get them to cross over without bumping into each other. Obviously, they can't. They always crash into each other. But if I do the same experiment and copy and I paste here, do the same experiment, but now instead of, so this is 1 + 1D. Instead, I say 2 + 1D. I take these 2 particles, I move them towards each other, and I want to get them past each other to the other side. Well, I can get them past each other without touching easily by just moving one around the other. Okay, so it's no crash. Now let's imagine having some linked world lines like this, and I'm going to look at this region here and ask whether I can unlink these rings without crashing the 2 strings into each other. And obviously, these 2 rings will crash. if I try to pull them apart, the two rings crash in 2 plus 1D. 2 plus 1 equals 3D. But if I'm in 3 plus 1D, they don't have to crash because I can just displace this region into the additional dimension, just like I did here. I displaced into the additional dimension and then push it through to the other side. And I can take an overcrossing and turn it into an undercrossing without having the two strings hit each other. So at 3 plus 1D, there's no crash. So that means you can always untie a knot in 4D. And that means that since there's no knots in 4D, it means the exchange operator is well defined. I don't have to give additional information about whether you went over or under, because over and under are the same. I can take an over path and turn it into an under path continuously. So that means that the old argument about just you having the exchange operator and exchange operator squared is plus or minus 1, that holds water in 3 plus 1D, but not in 2 plus 1D. Okay, there's another question online here, which says, is there a toy model to study anyons? Well, one is fractional quantum Hall effect with which is exactly solvable for V is, from a very special interaction, less than J delta R minus RJ. So some interaction like that. So fractional quantum Hall effect nu equals 1/2 or nu equals 1/3 with a derivative of a delta function interaction. That's exactly solvable without approximations. There's other toy models for anyons. One that's very, very popular is known as stringnet models. Stringnet models, or Levin-Wen models, or quantum double models. Another set is the Kitaev quantum double model. There's also the so-called Kitaev honeycomb model. This is a little less exactly solvable, but it's pretty much exactly solvable. So Levin-Wen and stringnet are pretty similar, almost exactly the same. Quantum double model is just another name for these, sort of more generalized. Kitaev quantum double, I mean, these are all sort of lattice models, which they're somewhat a little bit artificial. Kitaev quantum double model is basically a lattice gauge theory. And these are all pretty much exactly solvable models, which you can play around with without approximations. Are there further questions? We have 10 minutes to go before I turn into a pumpkin. Maybe I should stop there because if I try to start up something else, I'll go over my 10-minute deadline. And I didn't give you a break in the middle, so. Nothing else? Yeah, go ahead.
So we saw this nice construction of Laughlin with filling fraction 1/m, but what about some other fractions that are not of this type?
Yeah, so there's several different ways to do it. Other fractions. So so now it gets complicated. So there are so-called Haldane-Halpern hierarchy states. Haldane-Halpern states, which are pretty much the same as Jane states. And these are all so-called abelian anion models. And there's various different ways to do this. One way, the original Haldane-Halpern way, is that you start with your Laughlin state, then you put a lot of these quasi-holes or quasi-particles, the opposite charge excitations. These are anions. But then you take the anions and you put them in a Laughlin state and you condense them into a new ground state. And that makes another quantum Hall state. So you can get, so I forget how this works. So for example, if you take nu equals 1/3, and then you have the E/3 particles, and you take these and put them in a Laughlin state, So you let them form a state themselves. So they move around with their own dynamics, put them in Laughlin state. You can get nu equals 2/5 or 2/7, depending on if, and so forth, or 2/7, whether or not you're condensing plus or minus E/3 particles. But Jane has a different way of constructing the same thing, which looks perhaps a little bit more natural, which is to take any integer quantum Hall state and attach Jastrow factors to it, Zi minus Zj squared, and then project the whole thing to the lowest Landau level. Now, these account for a large proportion of the quantum Hall states that are observed experimentally, but there are others that don't fit into this. There are the non-abelian states, and these are perhaps the most interesting for quantum computing. States of which there are several that have been observed. So there's nu equals 5/2. Nu equals 5/2, 7/2. These are okay. There's various different ways to describe them, but they have even denominators, which is kind of interesting. These are for all of these Jane and Halpern states, they all have odd denominators for electrons. The 5/2, these are sort of unique in having even denominators. Nu equals 12/5 state is thought to be a so-called Reed-Rezai non-abelian state. There's let's see. So there are a couple of exceptions, and okay. So there's another question. Can you briefly explain the experiments part for anions? Unfortunately, I really do have to run in seven minutes. But let me try to say how it's done roughly. So the way it's done is you take a quantum Hall system and you use the fact that charges tend to run along the edges. Those are so-called edge states. You pinch down the bar like this. So the electrons live in the middle here. So this is the quantum Hall state. And then you send in charges along the edges. Now, they often run along the edges. Let me just get rid of this. So that's the electrons are sort of living in the middle. Okay. And then the charges can go along the edges like this, or they can get back reflected here. And what we're looking for interference between this path. It's basically the Fabry-Perot interferometer and this path. So you measure the phase by doing this interference here, you measure the phase of accumulated by going around this cavity. And then what you do is you add a quasi-particle to the center and you see how that phase changes. So this experiment was attempted for 15 years before it was finally successfully and convincingly done. And it's just in the last like 2 or 3 months, it's now been reproduced by 2 other groups. So it's pretty incontrovertible now that it works as advertised, and you pick up the right 2π/3 phase for adding a charge into the center. So that's roughly how it works. Okay, I'm down to 5 minutes before I turn into a pumpkin. Are there any other last minute questions? Anything else?
Hi, I have a question, and it's related with the detection of the anions. The problems are similar to the case of the detection of Majorana ferments.
Not exactly. So the physical system is quite different here. So actually, the 5/2 and 7/2 state are believed to have Majorana fermions, Majorana zero modes in them. The Majorana experiments that were publicized quite a bit are done in quite different systems. They're superconducting, semiconducting quantum wires. So they're really one-dimensional systems. And what people were looking for were evidence of a qubit state. When you have two of these Majoranas, and you put a big circle around them, it acts as a qubit. So there's two-state system. And so that, I mean, I would say that it's been problematic. They've been, even ever since, I mean, there were a bunch of retractions of papers trying to detect Majoranas, they're attracted for different reasons. I don't expect to see those retractions in any of these quantum Hall experiments recently. At least 3 of these experiments by, a bunch of experiments, they seem much more solid than what we saw in Majoranas. I mean, the Majorana people have come out with later experiments, which they say are more convincing, that haven't been retracted. But I haven't really looked into them that carefully. I don't think they're convincing, but they're trying to see something a little bit more sophisticated than we've seen so far with the anyons. So it's a somewhat different system. So the problems are I mean, they have their own problems. So, all right.